Hello, my name is Martin, and in this video, I will demonstrate the Similarity Mapping app at pdfitc.org. In this video, I will try to introduce the concept of similarity mapping to you, together with the scientific case for the data I will use for the demonstration. Then we'll go to pdfitc.org and explore the Similarity Mapping app, and then we will interpret the results of this together. So similarity mapping is a model-free method where we conduct a Pearson correlation analysis. That means for a data set of for a set of PDFs, then for each pair of PDFs, we calculate the Pearson correlation coefficient. And here, high correlation means the two PDFs are similar, which we interpret as that they represent similar structures. Then if we have low correlation, it means, well, the PDFs are dissimilar, not similar, which we interpret as dissimilar structures. So we can use this tool to explore correlations for a series of data or a data set. For instance, if we vary some variable during a material synthesis, or indeed if we conduct operando or in situ experiments, where we expect the PDFs to change over time, maybe due to some varying temperature, pressure, voltage, and so on. So the data I'm going to use for the demonstration is some of my own data, and it actually comes from a follow-up study. So I'll briefly try to explain or present the original study here. So it is concerned with titanium dioxide with rutile structure, which are incorporated into lithium-ion batteries. And Christensen and collaborators, they realized that during the galvanostatic charge discharge here, well, then the initial discharge profile is, well, dissimilar to the following charge and discharge profile. So it indicates some irreversibility in the material. So what they did is that they conducted an operando powder X-ray diffraction experiment to probe the long-range order in the material. And what they realized was that during deep discharge, they lost Bragg intensity. We can see that the Bragg deflections fade. And well, that is interpreted as a loss of crystallinity, which means that the length of structural coherence shortens in the material. And indeed, from beyond that point, it is hard to extract any structural information using this method. What they did then was that they conducted an operando X-ray total scattering experiment for paired distribution function analysis. And now they probe short range order. And here, in this experiment, they also observed the irreversible transition. However, now they can actually extract structural information where they actually can see how correlations change during the course of charge and discharge. So this basically just shows the power of total scattering and PDF analysis. Okay, in my follow-up study, I observed similar electrochemical behavior. I also observed similar phase behavior. Inspecting the PDF, you can see that we have some discontinuity here at deep discharge. And what does that reflect? Well, it reflects that we have a severe structural reconstruction. Another way to explore this operando dataset is to do a waterfall plot. And well, inspecting those PDFs, we can see that, well, the PDF for the initial material, the pristine material, we have atomic pair correlations further out in R, whereas during the initial discharge, the intensity decreases. So that indicates that the length of structural coherence shortens in the material. And indeed, that is in accordance with we observed in Q-space. And between these two PDFs, we have the structural reconstruction. And from that point, we can see that the PDFs are more or less similar. They resemble each other to a significant extent. However, this is just a qualitative way of exploring this. Let's instead go to pdfitc.org and explore this in a quantitative way. So we start the Similarity Mapping app. And here you can see that we can upload some files. We can state some threshold which is related to the Pearson correlation coefficient that we calculate using this app. We can state the R range for which we want to conduct the analysis, and we can state whether we have experimental or simulate data. If we click on the instructions, you can see in this paragraph what it actually means to state a threshold. Here you can see what it means to state the R range, and down here you can read about the files you can download after the analysis has been conducted. But let's just try to upload my dataset. So I choose all 42 files. I state no threshold or R range. It's experimental data, and we submit. So right now, my 42 PDFs are being uploaded to PDF ITC, and the correlation analysis is now being conducted. And in a few seconds, we should see 2 plots and a table. Indeed, you see 2 plots here, and well, down here you see a table. So the table here is the correlation matrix that has been calculated, and up here it's just 2 plots to represent that matrix. The only difference between these 2 plots is that over here you have then the matrix on an absolute scale from 0 to 1, whereas over here it's on a relative scale, so from 1 and to, well, the lowest Pearson correlation coefficient encountered in the analysis. Let's try to interpret the plot. So on this axis we can see that we have the first PDF up here, the last PDF down here, and on the other axis we have the first PDF here and the last PDF here. On the color bar you can see that, well, high correlation means deep red, and poor correlation, basically no correlation, means deep blue. If we see the first PDF's correlation with itself, so if we look on the diagonal or inspect the diagonal, we can see all of them are dark red. That's because we have perfect self-correlation. So, however, if we consider the off diagonal, we can see that during the initial discharge, well, we have some similarity between the first few PDFs. However, quickly, the dissimilarity is pronounced, and indeed, down here it is really pronounced. They are really dissimilar, as observed in the waterfall plot. In this plot, you also see some sort of a discontinuity. However, let's consider this block here, which is after the deep discharge, or after the order-disorder transition. From that point, you can see that all the PDFs resemble each other to a significant extent, as we also observed in the overview plot, right? However, it still seems like something is going on during the following charge, discharge, and charge. Or to realize what is actually going on here, let's try to start the app again. However, instead of uploading all the PDFs, let's only upload those PDFs that follows after the order-disorder transition. So for the first plot to the left, which is on the absolute scale, we should observe no difference. Indeed, we don't. However, over here to the right, where we have the relative scale, we can now see that the discharge state here, well, is somewhat different from the charge state here. However, it does resemble the discharge state here. So there seems to be, even though we had some irreversible disorder transition after at the deep discharge state, well, from there on, it seems to have somewhat reversible behavior. As a last demonstration, we'll try to upload the whole data set where we try to state the R range. Let's just consider from 30 to 50 angstroms. So that is, well, not a very local level, but a bit further out in R. And if you remember from the overview plot, we saw that during the initial discharge, the length of structural coherence shortens. So now we expect that the PDFs are more dissimilar, or at least they are dissimilar quicker during the initial discharge. And indeed, if we compare this plot here to this plot here, well, you see the dissimilarity. So that means the dark blue color, well, comes quicker in this case. So this was just a brief, it meant as a brief illustration what you can do by, what you can investigate by editing or setting the R range that you probe. Let's wrap up this video with some take-home messages. So hopefully I demonstrated that PDF ITC's Similarity Mapping app is a really great tool if you want to explore your similarity, the similarity of your data in a quantitative way. So it is a model-free Pearson correlation analysis. Since it is model-free, well, it's straightforward to do as soon as you have your data, which is really, really cool and useful. So indeed, it is a great way to explore your data or your structural changes in your data in a quantitative way. If you have, for instance, if you have phase transitions, and indeed, if you want to just explore whether those are reversible. So last thing from here is please go to pdfitc.org and explore your data. Thank you for watching.